He's going to be telling us about robust encodings of the black hole interior. And actually, let me pause to remark that we're aiming to make these 40 minutes plus 20 minutes, so there's plenty of time for questions. So if you have a question, just chime in, unmute your mic, or you can type it, and I'll try and find a appropriate time to stop Isaac and ask. Okay, so with no more interruptions, we have Isaac Kim. He's going to tell us about robust encodings of the black hole interior. Yeah, take it away, and we can start recording.
All right, thanks. Thank you for the invitation. So I'm going to tell you about this recent work with Eugene Tang and John Preskill. They're both from Caltech, and the title is Gaussian Radiation, Robust Encodings of the Black Hole Interior. Before I begin, let me just point out that there are already 2 talks given by one of the co-authors, John Preskill. Both were presented at KITP. And he actually goes through a lot of details, technical details on this paper. So if you're interested in the more details, then you should definitely check that out. And because there is this material on the internet already, I wanted to give this talk in a way that is complementary to John's by emphasizing more on what a small observer generally can't do when he interacts with a large quantum system. This will be sort of the main theme of my talk. And the rest of the talk will be very similar to John's, but somewhat more condensed due to the time limit. So it has been proposed in the 1990s that the inside and the outside of the black hole are perhaps not separate systems. Maybe they are described by the exact same degrees of freedom. This is known as the black hole complementarity. And this somewhat radical proposal has actually held up to some non-trivial tests, such as the Hayden-Preskill thought experiment. And for a long time, this proposal has been out there without too much trouble until in 2012, a group of authors known as AMPS proposed the Firo paradox. In the Firo paradox, you consider an old black hole that has been emitting a Hawking radiation for a long enough time so that more than half of its initial black hole entropy has been radiated away. So in that setup, according to the effective field theory, any near horizon mode B must be entangled with its infall-living partner B tilde. However, because if we assume that the formation and the evaporation of a black hole is a unitary process, because we have waited for a long enough time so that the radiation constitutes more than half of the entire system, we can conclude that B, this near horizon mode B, should be actually also entangled with the radiation. This is just a conclusion from quantum mechanics of a scrambling system. So it looks like we have a bit of tension going on here, and the tension is still following. So this mode B can be entangled with both B tilde as well as the early radiation. And one might say that perhaps this is okay because of the black hole complementarity, but the main issue is that there appears to be a single observer, the infalling observer, that can collect the early radiation and perhaps distill whatever is entangled with the B mode, and then capture the B and B tilde mode along his way falling into the black hole. And then in his pocket, he will have these 3 quantum systems, whatever is entangled with B and the B and also B tilde. So it looks like he can observe the violation of the monogamy of entanglement. And that is a problem. This paradox raised a lot of questions, but one of the more instructive examples to understand this paradox came from the thermal field double state. In this context, the quote-unquote radiation is the left side of the thermal field double state, and we can again consider a version of this paradox. So we again have a near horizon mode B, and its infalling partner B tilde. And in this picture, B and B tilde is entangled, and also B and the radiation is entangled. But that's actually okay, because B tilde can be evolved from B tilde prime. So you can say that B tilde and P tilde prime, They're essentially the same degrees of freedom. So they can't be decomposed into tensor product subsystems. So maybe this is okay. And certainly in the context of thermal field double, this is a coherent story. But you may wonder that for the evaporating black hole, whether everything will be still okay. So if you assume that the interior of the black hole is encoding the radiation, there are a couple of thought experiments that you can do. But before we do that, perhaps we should make things a little bit concrete and emphasize that the proper time between the event the infaller finishes collecting the radiation and the event in which the infaller crosses the horizon is roughly like order the black hole entropy to the raised to the 1.5 power. So in this is a finite amount of time. It's not an unlimited amount of time, but it's a long enough time that you can do certain amount of things. So you might wonder that maybe during this time, you may be able to extract whatever is entangled with the B mode from the radiation, and this could potentially lead to a paradox. There has been some work which was first advocated by Harlow and Hayden, and then by Aronson, and more recently by these Python's lunch people, that the complexity of decoding the Hawking radiations is maybe actually exponentially hard in the black hole entropy. There are a lot of evidences suggesting that this seems to be the case. And if that really is true, then the EMS argument in its original form becomes moot, because you cannot actually distill whatever is entangled with B from the radiation in the short amount of time that the observer has before he jumps into the black hole. So maybe that's fine, but actually, for the purpose of this talk, I would like to focus on a slight variant of this paradox, in which the infaller doesn't actually extract whatever is entangled with B from the radiation, but instead he applies a simple perturbation. You can think of it as like say a single qubit operator, let's say sigma x, acting on one of the early radiation qubits. And certainly the infaller has the capability to do that between event 1 and event 2. And this operation may be problematic. The fact that this operation may be problematic has been pointed out by the original AMS plus Stanford in 2013. So they argued that, okay, whatever this definition of the interior mode operator is, it must be a highly scrambled operator. And such operators generically have a order 1 commutator with any simple operator. And in fact, one can even go further. In fact, Papadopoulos and Berger proved that you can actually find always a simple operator which has a order 1 commutator with OB tilde. And this suggests that one may be able to alter the joint measurement statistics of the interior mode operator and the operator acting on D by applying this simple operator. So for example, you can imagine beginning with the following particular entangled state, which is the 0, plus 1, 1 state over, let's say, B and B tilde mode. And this state is specified completely by the fact that the expectation values of the operators, which is a tensor product of X, and also Z and Z, are equal to 1. And if you apply a simple operator to change the measurement statistics of these operators, you end up changing it into another state. And that change will be generically be by an order 1. And that would be a problem, because the joint state over B and B tilde can depend on what the infaller, whether the infaller applied the simple operator on the radiation or not before he jumps into the black hole. So semi-classically, the infaller is supposed to see the vacuum, which is unique. And it looks like we have 2 states which are not exactly equal to each other. In fact, they deviate from each other by order 1. And therefore, it seems like at least one of these 2 states must contain an excitation. So the main trouble is this. So there appears to be a simple experiment that creates an excitation behind the horizon, and then follower can actually fall into the black hole and see this excitation. And actually, the problem is significantly worse than this because uh, we have only considered a simple operator acting on a single qubit, but actually the infollower has a long enough time to apply a non-trivial quantum computation on the radiation. And the question is, how can you ensure this, the space-time locality between the interior and the exterior against an observer that has such capabilities? Okay, so it is important to note that this conclusion is based on a quote-unquote somewhat plausible argument that there is no definition of the interior mode that is entangled with both B while being space-like separated from the observer. Which brings us to our main contribution. We will see that we will see where this argument went wrong in a simple quantum mechanical model by providing an explicit construction of like quote unquote interior mode that satisfies criterion 1 and 2 simultaneously, albeit with an exponentially small error in the black hole entropy. And because we have a model, because in our model we see this interior mode encoded in the radiation while maintaining the space-time locality between this interior mode and what the exterior observer can do, we believe this result constitutes as a non-trivial evidence supporting the ER equals EPR proposal, or any proposal that suggests that the interior is encoded in the radiation. There are two important ideas behind our work, and I would like to spend a fair amount of time explaining what these ideas are. So the second one is something that Adam told us about yesterday already. It's the concept of pseudorandomness, which I will discuss again. But there's another very simple observation that will prove to be very useful. It's an observation that if you have a small observer has certain constraints on what they can do, So I'll get into that first. So as a preamble, I'd like to raise the following question. So suppose there are n qubits, and we want to apply an operator of the following form, which is a tensor product of Pauli operators. We choose either identity, x, y, or z. There are 4 to the n minus 1 such operators. And the question is, can you apply any such operator? And naively, the answer is yes. Obviously, these are not that difficult to implement. But I will argue that in certain situations, this is not always possible. And to understand why, we need to recall two important facts that we often neglect in physics, which is usually fine because neglecting these facts don't really these facts usually don't have many non-trivial implications, which is why it's okay to forget about them. But we'll see that they do, in fact, have a non-trivial implication if the observer is small. So these assumptions are, I believe, uncontroversial. One, the joint evolution of the observer plus the rest of the universe must be unitary. And second, the observer must have a bounded number of qubits. Perhaps a better way to say the second one is that the observer comprises of a bounded number of qubits. Let's consider the more familiar scenario. So we have Alice and Bob, and Alice is much larger than Bob, and Alice wants to apply any Pauli operator on Bob. Okay? You can think of Bob as a small quantum computer that are like available these days. Let's say like a 10 qubit quantum computer, and we are a macroscopic object. And although I didn't do the experiment, I strongly believe that you can apply any Pauli operator on 10 qubits. If you don't believe me, you can go ahead and run these actual experiments on this quantum computers. Okay, so that's that. But now we want to move to a different setup in which Alice is small, but that Bob is big. And again, we want to ask whether Alice can apply arbitrary Pauli operator of a choice. This is not always possible. This is actually not possible because we have assumed that the joint time evolution of Alice and Bob must be unitary. And so we can consider, for example, a unitary in which, depending on the internal state of Alice, she applies a particular operator O sub n. And you can clearly see that the cardinality of the set of operators that Alice can apply is at most 2 to the n sub a. Although, of course, she can also apply a linear combination of those things by being in a superposition state. And this conclusion continues to...
You're not stating this explicitly, but you're using the fact that Alice controls her initial state, but not the unitary that will implement.
That is correct, yes. The unitary that governs the time evolution is a fixed thing. And Alice's choice is, the only thing that Alice can choose to do is to change her initial state. That's correct. And this picture continues to hold, even in the presence of a large probe that Alice can wield. Again, in this case, the number of operators that Alice can apply is bounded by the Hilbert space dimension of Alice. Good. So the main takeaway from this simple exercise is that, generally speaking, provided that the unitary that governs the Alice and Bob's time evolution is fixed, Alice has a limited amount of free will. So the mental model that I have about this is like a human that is interacting with the Hawking radiation emitted by a solar mass black hole. So the entropy of that black hole is roughly 10 to the 77. And there are two kinds of experiments which sounds very similar but very different. One is Alice trying to apply a one body operator of her choice on these radiation qubits. And there are only, quote unquote, only 10 to the 77 such possibilities. And she certainly has the capability to do that, provided that she has more than 256 qubits. However, if she wants to apply like arbitrary Pauli operator of her choice, she simply doesn't have enough entropy to do that. So I hope I conveyed the following important point. So just because you can interact with some large quantum system in its entirety does not mean you can apply any operator on that system. So you really have to consider the unitarity constraint on the observer plus the observee, which in many cases doesn't really amount to anything. But in the context of the Firo paradox, a small observer is actually interacting with the big Hawking radiation. And this will come into play. Another note is that this constraint exists independent of how complicated of an operation the observer can actually apply. Recall that the tensor product of Pauli operators are very simple to implement. Just apply all these operators simultaneously on all the qubits. Now, I want to move to finally complexity, which is the main topic of this conference, and in particular about pseudorandomness. So I've already told you that Harlow and Hayden argue that it is exponentially hard to distill the BD tilde entanglement, the entanglement between the near horizon node and its infalling partner. And there has been a number of other arguments that argue that it's in fact very difficult to even establish any form of correlation between B and B tilde. And the theme of this second part of this talk will be somewhat similar to the first part, in that we will again consider the limitations of the observer, but now this limitation will not come from the size of the observer, but from its computational capabilities. So we will make a slightly different kind of hardness argument, which is motivated by Hawking's calculation, as well as a recent development in complexity theory. And although I think our hardness argument is morally very similar to these first two arguments, I think it's phrased in such a way that allows us to say more things. So to explain what we mean by pseudorandomness in our context, we will assume that the formation and the evaporation of a black hole is a unitary process. So we have a simple scrambling unitary quantum circuit, which we denote as UBH. BH stands for black hole, which given a shell of infalling matter produces some entangled state. We assume that we are past the page time, so the early radiation E is more than the half of the entire system. If you like, you can think of E as a subsystem which constitutes 99% of the qubits. So according to Hawking's calculation, any low point correlation function of E should be equal to that of the thermal radiation up to a potentially non-perturbative corruption. However, at the same time, when E is larger than HV, then E can no longer be thermal because it just doesn't have enough entropy, assuming that the initial state is a pure state. So you can ask what went wrong here. And by somewhat simplifying this setup a little bit, we can find a close analogy with a concept called pseudorandomness. So of course, a realistic description of this black hole formation and evaporation process must respect the charge and energy conservation. But we'll just simplify this a little bit by considering a quantum circuit that has no conserved quantities. And in the absence of the conservation law, there's only one thermal state, which is the maximally mixed state. So in this version, we can consider a scrambling unitary circuit with no conserved quantities. And after the scrambling happens, we collect 99% of the entire qubits. And then we want to determine whether these qubits are the actually mixed state, like maximally mixed states or something else. And pseudorandomness, of course, information theoretically speaking, this state has to be very different from the maximally mixed state. But the concept of pseudorandomness is it's a concept that tells us that there are certain situations in which, even though E is information theoretically different from the maximally mixed state, it is computationally indistinguishable from the maximally mixed state against an adversary who has a limited computational power. More precisely, we can formulate this assumption as follows, just to emphasize this is an assumption. We were unable to prove this, but we basically have two quantum states, rho B, which is the state that is created by this process, and we have another state which is maximally mixed state, the identity divided by the total dimension. And what you do is that you apply a unitary operator U, and then you measure a simple operator. By simple operator, I mean like a single qubit operator. And as long as you have a upper bound on the unitary, on its complexity, let's say the number of gates that you use is at most bounded by polynomial in the size of the remaining black hole, then we will assume that the difference between these two expectation values is at most exponentially small in the size of the remaining black hole. So this is an assumption. So you might ask, like, is this assumption warranted? So for the realistic black holes, we don't know. But at least for generic quantum circuits, we can ask later whether this is a reasonable thing. And indeed, we believe this is reasonable because there are actually efficient quantum circuits for which this E becomes computationally indistinguishable from the maximally mixed state, at least assuming certain cryptographic assumptions that there's a family of functions which are computationally indistinguishable from uniform random functions against any efficient quantum computation. So this is a work, a very nice work of Ji, Song, and Liu. One minor comment is that in this JSL's definition of pseudorandomness is actually much more involved, and in some, I think one could say that we sort of butchered that definition down to a very simple version. Because they actually even allow polynomially many copies, whereas our version can be thought as having like one copy of a quantum state pulled out from a certain distribution. But we won't actually need to consider those like polynomially many number of copies of cases, which is why we're just using this baby version of the definition. It's just simpler. So just to recap, we have learned two things so far. So one is that the small observer can actually perform a limited number of experiments. And the number of experiments that the small observer can do is bounded by the Hilbert space dimension of that observer. The second lesson is that it is possible to efficiently generate a pseudo-random quantum state. These are quantum states which are information theoretically nearly perfectly distinguishable from the maximum mixed state, yet prohibits any form of sufficiently computationally constrained observer from finding out this difference. So motivated by this fact, we will assume that the early Hawking radiation of a black hole, old black hole, is pseudo-random, and then we will explore its consequences. So this is our model. Again, we have a shell of inflowing matter. Okay, and then we have a black hole is formed, and then it has been evaporating for a long enough time. So E constitutes, let's say, 99% of the entire system. And then the observer comes in. He interacts with this radiation via this unitary. And again, the observer doesn't choose the unitary explicitly. He only does that implicitly by choosing its initial state, omega. And she also has access to a probe. So we have this big unitary. Our assumptions are the following. So we assume that the black hole is much larger than the observer. The E prior to applying this unitary is pseudo-random, and that this unitary has a complexity polynomial in the size of the remaining black hole. This is not to say that we are completely disallowing the observer from applying a more complicated operation. It's just that the kinds of things that we can say when UE has larger complexity is more subtle. The goal is to find a definition of subsystem B tilde, which is fully entangled with B, and at the same time that commutes with what the observer does. In order to do that, it will be convenient to characterize what the observer does. Usually, we think of an observer as someone who can apply explicitly some operator, but in our picture, the observer is applying something implicitly by choosing its initial state. So how can we characterize the observer's action? It's instructive to begin with a simple example, which we call as a control unitary model. This is a model in which, depending on the internal state of the observer, which is n, the observer applies a unitary operator of her choice, say U of n, on the probe and the radiation. Of course, so in this version, the observer and the probe and the radiation becomes decoupled after the observer applies U sub n, provided that the observer begins with one of the computational states. But more generally, of course, the observer can be entangled with both the probe and the radiation. And the most general case that you can think of can be thought as a quantum channel acting on piece of P and E, where this quantum channel depends on the initial state of the observer, omega O. And here we can view this as a probabilistic mixture of states in which the observer applies E sub A, which are the Krauss operators of the channel. And the probability of that particular branch happening is proportional to the normalization of EA rho PE EA dagger. Our main result is the following, which is the existence of quote-unquote mirror operators, which is very reminiscent to the Papadoudimas-Raju construction. So suppose that the observer has a choice of either applying a perturbation or not applying a perturbation. So that's what I mean by E sub A including I. Then for any operator T that acts on B, that guy, for T, there is a mirror operator T tilde such that, number one, T tilde acts as an entangling partner of T. What I mean by that is that the action of T here can be pushed to this T tilde. That part is completely trivial. You can always do that. The non-trivial part is that you can find a definition of T tilde which satisfies not only this first condition, but also a condition that T tilde commutes with E sub A for all E sub A up to a very small correction. And this is what we call as the locality. Even though T tilde and E sub A their commutator does not vanish in the entire Hilbert space, they do on this particular state. I'd like to briefly sketch the argument. For more details, again, I recommend watching John Presco's talk. The argument consists of 3 parts. In the first part, we make the following observation. Because the radiation looks maximally mixed to a small observer with limited computational power, B must be decoupled from the observer. I believe this is an intuitive statement because here O can be thought as a sort of a measurement record of the observer after it interacts with the probe and the radiation. And the pseudorandomness condition implies that independent of what the state of the B is, the observer won't be able to gather any information about this state of B. And so it's plausible that you can, it's reasonable to expect that the state of O and state of B is decoupled upon tracing out this, the remaining black hole and also P and E. And this is actually a very simple exercise that you can do, and the end result is this one. So the density matrix of OB is very close to being a factorized state with an error that decays exponentially with the size of the remaining black hole, provided that both O and B is, their combined subsystem size is parametrically small compared to the size of the remaining black hole. The second part of the argument involves a very simple observation. So recall that we have been considering this particular state, which is the state over the radiation, the remaining black hole, and the near horizon mode B. We can view this 3-legged tensor as a map from B to EH by simply pulling down this leg B downward and just calling it as a B tilde. So one could show that provided that the unitary UBH is a scrambled unitary, this map can be very well approximated by some isometry. And whenever you have an isometry, you have an encoding map of a quantum error correcting code. And then we can use powerful facts known about quantum error correction to infer the properties of this code, which we can translate back to the property of this state by simply moving from the right-hand side to the left-hand side. And the fundamental fact, there is a fundamental fact in quantum error correction which will prove to be very useful, and it's the following fact. So suppose we have already shown that this B mode is decoupled from the environment, which in this error correcting code picture implies that O learns nothing about the logical information about this B tilde. If that happens, then the fundamental fact in quantum error correction states that there is a recovery operation acting only on P, E, and H, basically the complement of this O, such that whatever error caused by O can be recovered by this recovery channel. And then, as a third part, we were able to prove something which we believe is new to the best of our knowledge. We call it as the theory of ghost logical operator. We were able to show that for any quantum error correcting code, if a code can correct this channel, which can be morally thought as doing nothing with 1/2 probability and applying a quantum channel E with 1/2 probability, then there is a complete set of logical operators, T, consisting of T, such that all these operators commute with all the error operators, E sub A, on this code subspace. And in my opinion, the fact that this is possible was really not obvious at all. There were some hints that this was possible in the context of operator algebra quantum error correction, But in any case, we decided to refer to these set of logical operators as a complete set of ghost logical operators. Ghost logical operator because these are operators that act on the physical space that that's sort of there, but it's unaffected by any of the error operators. And with a bit more work, one can actually extend this statement to the approximate setting. You can check out the details in the paper. After accounting for all the correction terms, we obtain this bound. It's essentially the same equation, but more nuanced. The bottom line is, if the observer and the number of near horizon modes that you consider is small compared to the size of the remaining black hole, then the commutator on the code subspace is again exponentially small. And because this T, if you believe these T's are the operators that are associated to the interior, the infalling partner of the B modes, and if this E sub A's are the operators that the external observer can apply, then you would conclude that the causality between this interior mode and what the observer can do outside is well respected. It can't do the amount of non-local signaling that you can cause is exponentially suppressed. Just to recap, this is the more holistic view of the sketch argument. So we have already established that the environment learns nothing about the logical information, which implies that the code can correct the errors that are induced by this environment/observer. And this second result implies the existence of a complete set of ghost logical operators. And once you map these ghost logical operators back into the state picture, they can be interpreted as the mirror operators. I would like to make some comments about state dependence. There is still I would say, a controversy about state dependence, whether it's okay to do this. And our construction of the interior mode depends on the initial black hole microstate. And in that sense, it is state dependent. You might ask whether this is okay or not. I don't have an answer to this question, but what I do want to emphasize is that state dependence is not this like magic bullet that solves all the problem. Even if you use state dependence, but that alone is not enough to resolve the firewall paradox. Now, why is that? To see why, you can consider a small observer which has a huge computational power, basically unlimited computational power. And for such an observer, surely she can directly apply these mirror operators or ghost logical operators, depending on your point of view, directly on the radiation/probe. And such an observer can certainly create an excitation behind the horizon at will and observe it. To see why, you can consider two cases. The case in which the observer does nothing and jumps in this case, she's supposed to see the vacuum. In the second case, the observer applies the ghost operator and jumps into the black hole. The point is, when she does the second thing, she only changes the logical information and you're still in the code subspace. And therefore, the entanglement between B and B tilde mode, whichever operator you use for the B tilde mode, must have been altered. Therefore, if the observer sees a vacuum in the first case, then she has to observe an excitation in the second case, because basically the entanglement between B and B tilde has been changed. It's also instructive to consider a different limit in which we have a big observer, which has limited computational power. So one may be able to bring in a large number of ancillary qubits and then simply swap the radiation qubits with these ancillary qubits. In this case, now the near horizon mode must be entangled with the ancillary qubits and not entangled with the radiation qubits. And you can ask, can you create a firewall this way? Well, again, I don't know, but I think it's important to remember, I think it's important to formulate a paradox in an operational way. And I found it difficult to formulate a paradox in this setup because for such a big observer cannot simply dive into the black hole without causing a significant back reaction to the geometry. So maybe there is a version of the paradox there, but we just don't know. So if you don't want to change the geometry too much, then you should only throw in a small part of this observer. And that part, for that part, our analysis certainly goes true. And it will be decoupled from B. And as such, there is again a complete set of ghost logical operators for that small part. Of course, this argument applies to in the presence of arbitrarily large probe, which suggests that in order for the effective field theory to work well, perhaps not only do we need low energy and low curvature, but also low rank and low complexity. Perhaps this is the main lesson of our study. Okay, so I want to make one final comment and go to the conclusion. So one might ask the following question. So the observer in the exterior cannot manipulate the interior efficiently, but an interior observer should be able to do that fairly easily. So as a sanity check, we asked whether one could actually efficiently manipulate the interior given access to BH. This question was actually raised by Juan Malacena. And thankfully, we found that for any operator V acting on B, we could apply the mirror of B by an efficient and deterministic quantum circuit. So I would say the basic sanity check has been done, although more studies in this direction would be desirable. I think there are many ways to view our result, but personally, my take on our result is that the black hole is a powerful error correcting code that can protect quantum information against low complexity errors. These are very different types of errors than what we typically consider in quantum error correction, where you apply like merely factorized errors on all the qubits with low strengths. Instead, here the environment can cause a highly correlated error on more than half of the entire system. The catch is that there is a part of the entire system that the environment cannot touch, but that part can be very small, like let's say 0.001%. And yeah, so certainly the existence of such a error correcting code is new and interesting. And but depending on your point of view, perhaps you're interested in these other takeaway messages. Okay, so I'll give you about a few seconds to read that. And I'd like to end with the provocative thesis as suggested by the organizers. So I prepared two theses, for one for the computer scientists, one for the people who are more interested in quantum gravity. The computer science conjecture is that perhaps random quantum circuits using like with depths that is super logarithmic, if you apply that to a simple state, then perhaps with very high probability, no quantum circuit using a polynomial number of gates can differentiate any finite fraction of the subsystem from maximally unique state. I asked this to my computer science friends, and they said they were unable to disprove it, but they told me that it's very hard. But it'll be good to know. On the quantum gravity side, our work, in my opinion, seems to suggest that the radial direction in the bulk may be a measure of how well the bulk quantum information are protected from not just erasures, but also low complexity errors. And it would be good to understand if one could understand the entanglement, the bulk locality in the entanglement shadow with this idea. So with that, I'd like to end my talk. Thank you.
Okay, let's all unmute and thank Isaac. And we have plenty of time for questions. So.
Isaac, I had a question. This is very nice, but I was confused about the first part of your talk. What role is played by sort of the limited number of bits of the observer? because, okay, that's going to upper bound the cardinality of, you know, the set of different unitary transformations that that observer could apply. You know, that's certainly true. But, you know, if we pick some explicit unitary, like, you know, the one that, a unitary that would decode something interesting from the Hawking radiation, then, you know, very plausibly that does have a short description. So then it seems like the real issue there is just the circuit complexity, right? So why not rely on only the second part of your talk? Like, why do you need the first part?
It's related to this part of my slide. So let's consider a big observer with a limited computational power. So like let's say we have n, let's say the number of qubits in the Hawking radiation is n. We bring in n fresh ancillas, all initialized to the 0 state, and then we swap the radiation qubits with these 0 states. If we do that, let's call this ancillary qubits as the probe. After we do that, certainly the B mode should be entangled with the probe, not the early radiation. So this is like a low complexity operation that it can apply. And one might argue that this way you created a firewall, right? Because, well, there's no entanglement between the radiation and the B mode anymore. But we still want to say something non-trivial in this case. And the thing is, if we consider a small observer as part of this probe, for every small observer, you actually cannot distill the partner mode of B. So like in some sense, the key statement, the key point is that if you have a small observer with limited computational power, that observer seems to be space-like separated from the B tilde mode. But if you consider a large observer with limited computational power, it seems difficult to ensure the space-time locality between that large observer and the B tilde mode.
I see. Okay, thank you. But by the way, I mean, you were talking about, you know, the analogy here to quantum error correction, or more than an analogy, really. But I mean, an ordinary quantum error correcting code would not protect against arbitrary polynomial time operations, right? So you're really saying that this is something much more powerful than an ordinary quantum error correcting code. Is that right?
Well, it's not a so the error model is not an entire set of like polynomial time quantum computation though. So in order to correct this error, you need to, I suspect, you need to know the actual time evolution that governs the environment and your system. The parameter that, of course, if the environment is no qubit, it has 0 qubit, then you can just reverse this, trivial. But it becomes non-trivial if the size of the environment is large but bounded. So if it's bounded, then we can still correct this.
Okay, thanks.
I didn't understand why the generalization in the definition of pseudo-randomness to many copies isn't relevant. Couldn't we imagine a version of the paradoxes that depend on experiments on n copies of a black hole in identical states?
I suppose we could, but we simply did not consider those possibilities. I would be curious to know what kind of new things we can say by invoking those paradoxes though. I'm not sure like what the main lesson would be by invoking many copies that we couldn't learn with a single copy.
And maybe I can take this chance to ask a question. So I was wondering about the existence of these unitaries that or they're efficient, but they lead to pseudo-random states. Is there any ingredient of fast scrambling in that at all, or is it just example by example basis?
It's hard to say. Let's see. It's unclear if fast scrambling implies that you get the pseudo-random states. It's just unclear. I don't know. Like all these proofs of pseudorandomness, it's basically based on some computational hardness assumptions. But like fast scrambling, you don't need that. I mean, at least for certain families of quantum circuits, you can argue that with high probability you have a fast scrambler. But to prove that you can get pseudorandomness, it looks like this is a much more difficult thing to prove.
Sorry, what's the definition of fast scrambling that you're using again?
That for any let's say any finite, for any like a subsystem of size, let's say less than 1/3 of the entire system, becomes maximal entropy up to some error, like let's say 1/poly n in like order log.
In that case, taking a random stabilizer circuit, I believe, would be a counterexample to that.
I see. Yeah, that's
right?
a good point.
That will be
will
be a scrambler, and it will not be pseudorandom.
That's right. I agree. Yeah.
Okay.
Good point.
Okay.
Thanks.
Can I ask a kind of an elementary question? So if you think that the early Hawking radiation is pseudorandom, does that just purely descriptively, independent of what observers can or cannot do?
That's right.
Purely descriptively, would the interior mode still be entangled with the mode that's on the horizon or the late time Hawking radiation? So I'm just asking whether purely descriptively there will be a violation of entanglement monogamy. Does the question make sense?
Let me just answer, and you can tell me whether it makes sense or not. So in this picture, we're not assuming a tensor product structure between the B tilde mode and the early radiation. So there is no violation of the monogamy of entanglement because B tilde is inside of E. But the main point of the talk is that so like you solve the monogamy of entanglement problem that way, but then you have this non-locality problem. And the goal of the talk was to resolve this non-locality problem.
Thank you.
But as soon as, yeah.
Okay, if there are no final questions, then why don't we thank Isaac again